Okay. So we're looking at a tetrapeptide, histidine, glutamic acid, cysteine, and lysine. So it's histidyl, glutamyl, cysteine, lysine. Histidine is the one with the imidazole side chain. So it's got this group. CH2 group. And it can be protonated here. In our textbook, it's 6.1, but on the sheet I gave you, that's 6.0. Glutamic acid has its side chain as the carboxylic acid, two CH2 groups, and it can be deprotonated to get the carboxylic acid, and this pKa 3.7. Cysteine has the thiol, and it can be deprotonated to get the thiolate ion. And this pKa 8.3, and then lysine has an NH2 group with 4 CH2s, and it can be protonated pKa, this is 10.5. And then we also need to know what the carboxy terminus of lysine looks like. We know that would have a COH. This pKa, I think it's 2.2, is that right? 2.2. And we also need to know what the N terminus of histidine would look like. And that pKa is 9 point something, 9.3 maybe, 9.2. So all four of these side chains are actually potentially going to be active at physiological pH. This one will be deprotonated, as will this one, and this one will not be protonated. Right? This hydrogen will not be present. The other three will be present. So this will stay there. This one will be protonated because 10.5. And this N will also stay protonated. So if we want to draw it at physiological pH, we've got our NH3 group. On the N, 1, 2, 3, one more. Got that group. Deprotonated, and then we're going to stick the side chains on there. I want to make sure it stays as stereochemistry, so in this case, we need the hydrogen back. So over here, we're going to put our CH2 and then our histidine ring. That it's going to be neutral. Here we're going to have our glutamic acid deprotonated. Here we're going to have our sulfhydryl group protonated, and here we're going to have our lysine protonated. So it's net neutral because we have two ammonium groups and we have two carboxylate ions. So we would expect that our isoelectric point will be somewhere close to the physiological pH of 7.4. The maximum positive charge. If we protonated everybody, the histidine and the 2-carboxylic acid would be +3. So we've got 6 equilibria. The maximum negative charge will be -3. And maybe you don't need to write all these out, but I'll just do it for completeness. These two are the ones we want. They're the middle two. So the first proton that comes off is this one. The second proton that comes off is the side chain. Third, the proton that comes off is the one that was on the protonated histidine. Fourth proton that comes off is the sulfhydryl group. Then the N-terminus. And the last proton that would come off would be the side chain of lysine. The only side chain that's more basic than lysine is arginine because of that guanidinium group. So we're going to add these two together and divide by 2. And the isoelectric point should be 7.15 or 7.2 if you use 6.1 from the textbook. This table came from like a company that sells a bunch of amino acids. So fairly straightforward. Hopefully you remembered the 4 amino acids that matter. Histidine and cysteine are important amino acids in, well, cysteine is an important amino acid for several reasons. Because it has this SH group, and there's an easy thiol disulfide redox reaction where the SH group can turn into a disulfide. That's the amino acid that's involved in protein kind of folding, where you have those disulfide links holding things together. Insulin, for example, consists of 2 different peptide chains, but they're held together by disulfide bonds. Hair curls when disulfide bonds are formed, and then when you break those disulfide bonds, your hair will straighten. So that's important. And cysteine is also an important element in the catalytic triad of some proteases. There are serine proteases where serine is involved, and there are cysteine proteases where cysteine is involved. They all have histidine and aspartic acid in them as well. And we'll be talking about a couple of those different serine proteases as we go further into the various things that you can use to find out information about the primary structure of a peptide. Okay, so let's talk more about these reagents. You can find out things about peptides. What reagents did we introduce on Tuesday that we can use to find out things about peptide structure? We introduced 3 of them. One was just concentrated HCl, which we used to cleave peptide bonds. Right, that's no surprise. Amides cleave with concentrated HCl. And then you said what, Dansyl chloride? Dansyl chloride is a naphthalene ring that has a dimethyl amino group on one end and a sulfonyl chloride on the other end. And what do we use Dansyl chloride for? What can we find out about an amino acid? What does Dansyl chloride do? It's actually the same thing that the next one does. It's OPA, ortho-phthalaldehyde. benzene ring with two aldehyde groups adjacent. Both of these reagents do the same thing, which is they tag the N-terminus with a fluorescent group. On the nitrogen, in the case of Dansyl chloride, it's a nucleophilic acyl substitution. Forms a derivative that looks like that. And in the case of ortho-phthalaldehyde, it's a little more complicated. But both of them have introduced a fluorescent group attached to the nitrogen. So we use these to figure out what the composition is, the amino acid composition. How many of each type of amino acid are present in the overall protein, which amino acids are present. That can be useful, just that information alone, because the secondary structure, whether proteins tend to form beta sheet structures or alpha helical structures, depends to some extent on which amino acids are present. If you have a lot of aromatic amino acids present, then beta sheet structures can be inferred. If you have proline in there in large quantities, proline tends to introduce twisting into the DNA, or into the protein rather, and that might indicate that there's some alpha helix present. There are two other reagents we already talked about. One is Sanger's reagent. Which is fluorodinitrobenzene. Dinitro. And the other one that we already talked about is hydrazine. Simply H2N and H2. And these allow us to tell not just what amino acids are present, but where one of those amino acids is. Sanger's reagent, fluorodinitrobenzene, identifies the N-terminal amino acid. Hydrazine allows us to identify the C-terminal amino acid. So we can figure out what's on the ends of our peptide with these two reagents. This one is an ipso substitution. At the N-terminus. And this one is nucleophilic acyl substitution to cleave all the peptide bonds. But importantly, this one, when you do that nucleophilic acyl substitution to cleave the peptide bonds, you don't get out the free amino acid. You actually convert them to hydrazides. So the C-terminal amino acid stays the amino acid, but all the others get converted at the C-terminus into the hydrazide. Those hydrazides have very different properties polarity-wise, so you can separate all those hydrazides out and identify just the C-terminal amino acid. This one tags the N-terminus, and then after you've tagged the N-terminus, then you cleave them with HCl. and all except the N-terminus become the free amino acid. Whereas the N-terminus has been tagged with this group. So now we have carboxylic acid that's got this group attached to it. Very different polarity properties, right? That's a neutral molecule. It doesn't exist as a zwitterion, whereas all the other amino acids are free amino acids that are zwitterions. We can easily separate that one from all the others. So just for review purposes, we should probably talk about the mechanism of reaction of those two things. They're both fairly simple. They're mechanisms you've seen before. So if you take a dipeptide, for example, let's use a very simple dipeptide. We'll just use glycosalanine or alanyl glycine, sorry. Ag. Right, so we've got one glycine with no side chain and one alanine with the CH3 group. There's always in equilibrium with that some of the negatively charged species. So there's always a little bit of free amine present. Obviously, there's always in equilibrium some of the +1 species as well. But this is what we care about. This is what's going to be doing the reacting with our fluoride nitrobenzene. So what would be the mechanism? It's important to actually write out the nitro group because we're going to need the electrons that are associated with the nitro group. So what would be the mechanism if you were asked for a mechanism here?
I'm confused with your chalk resonance thing. Where the heck did the H on the OH come from? Because there's a whole extra H.
Oops. No, we're right. Right. It's always equilibrium in solution. Right. We can deprotonate both to have a -1. We can protonate both ends to have a +1. So I'm just showing you this is basically the 0 to +1 equilibrium.
Oh, equilibrium. Sorry, I thought it was the other one, the resonance arrow.
Yeah, not resonance. These are equilibrium. Sorry, I made that unclear. But it's always this one that we care about, the one that has the free amino end, because we need that nitrogen to have a nucleophilic lone pair in order to do an ipso substitution with this reagent. You can actually react a peptide with Dansyl chloride before cleaving them, and only the N-terminus would react with Dansyl chloride because this lone pair isn't nucleophilic, since that lone pair is resonating with the oxygen from the amide. So knowing that this is an ipso substitution, right, we've got the nitro groups in the 2 and 4 position, which is where they need to be to help delocalize that negative charge. We're simply going to come in and attack the benzene ring where the leaving group is, push our pairs of electrons down so we can delocalize them out onto nitrogen, or onto the oxygen rather, of the nitro group. And we could also delocalize them out onto the other nitro group if we wanted to. There's lots of different resonance structures for this. It's annoying because the molecules are large, but big molecules behave the same way as small molecules. So step 1 is the nucleophilic attack. What's step 2 of the ipso substitution? Come back, push out the leaving group. So now this pair of electrons will come back in from the nitro group. We'll regenerate aromaticity and kick out fluoride. In theory, I suppose that's reversible. In practice, not really. And then all we have to do is a proton transfer reaction to take this hydrogen off. I'm going to use fluoride as the base just because fluoride is a simple thing to draw, right? So we have nucleophilic attack, loss of leaving group, and proton transfer to generate HF and our tag amino acid, tag peptide rather. All right, these are ZO2 now because I don't need them. Now we cleave with HCl. We treat this with concentrated HCl. And we get a cleavage of the peptide bond. So what we get is glycine, and we get the tag alanine. So we can identify that the alanine is the one that got tagged and not the glycine, because we can use an authentic sample of this tagged alanine, which will have a distinctive retention time on HPLC, a distinctive RF value on TLC. Right, so we use either HPLC or TLC usually by some kind of chromatography. I'll just leave it at that. Could be thin layer chromatography or HPLC. So that's pretty simple, right? It's just the same three-step mechanism that you're used to if you have a neutral nucleophile doing an ipso substitution on an aromatic compound. And you can remember that this is an ipso substitution because you know that these deactivating, resonance deactivating groups like nitro and sulfonyl tend to make the ring susceptible to nucleophilic aromatic substitution. So that's pretty straightforward and helps us determine what the N-terminal amino acid is. The mechanisms that you're seeing are really not new mechanisms, right? There's no especially new mechanism associated with these biochemical molecules. Your main task is to recognize the reagents when you see them and know what that reagent is going to tell you. What piece of information can be gathered from that. So let's take that same peptide. And this time we're going to treat it with hydrazine. What do you imagine hydrazine will do if it confronts a peptide? And again, we have alagly or ag. So you notice that with the Sanger's reagent, we tag the N-terminus, but then we do have to treat it with concentrated HCl to break all the other peptide bonds in order to free up all the other amino acids except the N-terminus as the zero ionic forms in solution. But since those are salts and the other one isn't, right, zero ionic salts, it'll be easy to distinguish them. So if you were hydrazine, what would you want to do in the presence of one of these? first thing you'd want to do is take that proton off, right? So there's always going to be an equilibrium where hydrazine just gets protonated, but that's not productive. So we're not going to draw that. What else might hydrazine do? It can attack one of the double bond O's, but only one of the double bond O's. It can't attack the other one.
Well, it's going to attack the one that doesn't have a negative right next to it.
Right. So amides, although they're pretty unreactive, are a lot more reactive than a carboxylate. So importantly, it won't attack the C-terminus. So like the other mechanism, the first step is nucleophilic attack. But it's nucleophilic attack on the peptide. I'm going to draw an extra long bond here, just so we can not have the hydrogens right on top of each other. So what's step 2? Step 1 is nucleophilic attack on the carbonyl group. What's step 2 usually when you've done a nucleophilic attack on the carbonyl group? Generally push out a leaving group. This is a shit leaving group. Right? So that equilibrium would lie way towards this side. When you're doing an amide cleavage, you have a shit leaving group. Why did we manage to get that to leave? We promised it a proton. We said, you know, leave now. You can have the proton. This is going to be effectively irreversible because that proton is so much more acidic. So we get that, and we get this. There's no reason for this to stay protonated now because we don't have the negatively charged carboxylate within the same molecule. So now we're going to get another proton transfer, generating the free amino acid as a deuterion and generating the neutral hydrazide. And then we separate those because we've got neutral molecules and we've got a deuterion. So at that point, we could actually just stick them on an HPLC column. This one is going to come off at a distinctly different retention time than all the others, and then post-column derivatization would allow us to determine what amino acid we've just generated of the C-terminus. So that's great. We can determine which one's on the N-terminus. We can decide which one's on the C-terminus. But if you've got a long protein, just knowing the two ends doesn't really help you very much. So we need some additional reagents that are going to give us some more information than just those. What was I at? 6? Another reagent that allows us to determine some information about our peptide is phenyl isocyanate, or PITC. This reacts with peptides in a reaction known as the Edmond degradation and allows us to determine up to 50 amino acids, I think, now on the N-terminal end in sequence. So it does more than just tag the N-terminus. It actually breaks the peptide bond as well. And it cleaves just the adjacent peptide bond and kicks out a new N-terminus. So if you can monitor the reaction over time, the first amino acid that comes off will be the N-terminal amino acid, and then the next amino acid that comes off will be the next one in from the N-terminus, and then the third one to come off will be the third one in. And it's complicated only by the fact that it doesn't take all of the first one off before it starts taking the second one off. So you kind of have to keep track of multiple compounds at the same time. So the question is, how does Pitc react with the N-terminus of an amino acid, or a peptide rather? If you had this one, again, right, we need the free amines, and you had phenyl isothiocyanate, how would you think about getting it to react? It's going to attack the carbon, and it's going to push a pair of electrons out. And I've pushed them onto the nitrogen because the nitrogen is adjacent to the benzene ring, so that's benzylic. And now we're going to do some proton transfer reactions. It's typically run at an acidic pH. So we're going to protonate this first, and then we're going to deprotonate that. And I'm just going to use the ammonium group, right? Basically the conjugate acid of the amine. Proton transfer. We don't really need all of these atoms, but put them in there anyway just for completeness. And then that's going to take the proton off. So we've done that in 3 steps. Nucleophilic attack, and then 2 proton transfers to take the proton and put it on the nitrogen, and then remove it from the nucleophilic end. What kind of reaction is this? What class of reaction does this one fall into? This is a nucleophilic acyl addition across the CN bond. So that has tagged the N-terminus and converted into what's called a thiourea here. This is a thiourea. Because it's a CS bond sandwiched between two nitrogens. Regular urea has a C double bond O sandwiched between two nitrogens. But that thiourea is actually unstable and reacts intramolecularly, which means it's fast. And we can understand how that thiourea is going to react by applying our usual rule of organic chemistry and drawing the resonance structure. So we can draw a minor resonance structure for this. Like that. And has significant negative charge on the sulfur. There are two good reasons why that should be a fairly significant resonance contributor. One is that carbon-hydrogen, or that carbon-sulfur rather, pi bond was weak to begin with because of poor orbital overlap. And the other is because this pi bond is now conjugated with the benzene ring, so that extends our pi system. Right? We've got an extended pi system here. The CN double bond should be stronger than the CS double bond because of better orbital overlap anyway. So this is going to be a significant resonance contributor. And now we can count to 5. Sulfur is 1. And realize that this carbonyl carbon is just 5 atoms away from the sulfur. So kinetically, it would be quite favorable for the sulfur atom to attack it. In an intramolecular nucleophilic acyl substitution. And generate that if I didn't mess up, looks like that. Got our 5-membered ring. So that's the nucleophilic attack part. I guess I should write the step is just the nucleophilic attack. The next step will be the same as it was with hydrazinolysis, where we kick out our even group. Proton transfer step. Generate something that looks like this. So CH3 group there. Where's the draw? And we've got a new N-terminal. Very similar hydrazinolysis, except that the nucleophile is now the sulfur atom, and it's an intramolecular reaction. These rearrange in the presence of acid to form a more stable compound. We're not going to talk about the mechanism of that because it's a shit ton of steps. But in an acid, there'll be an equilibrium where this rotates, and what you form is looks like this. So we're basically cleaving the thioester and forming an amide in its place. The net effect, you'll notice, is to basically add the amino acid across the carbon-nitrogen bond. So this was the carbon-nitrogen bond of Pitc. You know that under acid conditions, esters are cleaved in 6 steps, the reverse of the Fischer esterification, and amides are formed in 6 steps. So basically what you're doing is a 6-step mechanism to cleave this thioester. It starts with protonating this oxygen and then attacking the carbonyl with water and continues, and then the nitrogen acts as a nucleophile. Sulfur is the better nucleophile, which is why this intramolecular reaction goes with the sulfur acting as the nucleophile to cleave the peptide bond. But this is a more stable compound. This compound is called a phenylthiohydantoin, and you can buy the phenylthiohydantoins of every amino acid. And those are readily identifiable by their retention time on HPLC. So you can figure out what the R group was here. Right? So this was alanine at the N-terminus. But because you keep cleaving, right, you get this molecule out, and then you've got a new N-terminus. The new N-terminus can react with more Pitc, and you'll generate the phenylthiohydantoin of the next one. In this case, it would look like this. And so alanine comes off first. Lysine comes off next. And that would generate another N-terminus if we started with a tripeptide, and then that third N-terminus could react. Maybe it's serine. Serine would come off next. The problem is not all of the alanine has come off before the lysine starts coming off, and then not all the glycine has come off before the next one starts coming off. So you're limited by the sensitivity of your instrumentation and how quickly you can analyze it over time to see which one comes off and what order they come off in. Especially if the 4th amino acid is the same as the first one. Now you've got to distinguish between the remaining cleavage of the first one that's still going on and the new cleavage of the 4th one. So instrumentation has gotten a lot better, detection limits have gotten a lot better. So we're able to go further in than we used to be able to. In practice though, in order to start identifying the gene that codes for that protein, you don't really need to know very far in, because every amino acid is coded by a triad of nucleosides. So if you know that alanine is the first amino acid and glycine is the second amino acid, that actually gets you 6 nucleotides. And to develop effective primers for polymerase chain reaction to try to amplify a gene, you usually don't need more than about 12. So if you can figure out what the 4 amino acids at the end are, you've got 12 nucleotides, and you can synthesize that primer and try to start finding the gene. Often the way proteins synthesis sequences are actually determined is not by directly sequencing the entire peptide, it's by sequencing pieces of the peptide, figuring out what gene codes for it, and then if you can amplify that gene and sequence the DNA, you know based on the DNA sequence what the protein sequence would be, because we know what 3 nucleotides code for every amino acid. So the Edmond degradation is more useful than Sanger's reagent because it doesn't get you just one at the end, it gets you multiple N-terminal amino acids. It would be really nice if we had a reagent that would do the same at the C-terminal end. So instead of just knowing the C-terminal amino acid with hydrazinolysis, we could actually get several from the C-terminus. And there is no chemical reagent, but there's an enzyme that does it. Carboxypeptidase A cleaves peptides at the C-terminal end. So the first one that comes off is the C-terminus, and the second one that comes off is the next one. And then we can tag the amino acid. And identify them. The mechanism for how carboxypeptidase A actually does that cleaving of peptides from the C-terminal end is not something I'm going to talk about, because that's protein structure. You have to know what the structure of carboxypeptidase A is, so that's the kind of thing that you learn in biochem. But the important thing is it cleaves the C-terminal peptide bond first. Releases an amino acid, a new C-terminus, then it cleaves that one off. So the amino acids come off one by one. Again, just like with the Edmond degradation, you don't get all of one off before the next one starts coming off. So it's a matter of how sensitive, how quickly you can analyze it and how sensitive it is for detecting the new one that's coming off in the presence of the old ones that have come off. So we can now get several amino acids on the C-terminal end, several amino acids on the N-terminal end, design primers that will code for that gene, and then try to figure out where that gene comes from. This is great if your peptides are short. If your peptide is only like 20 or 30 amino acids long, the combination of carboxypeptidase A and the Edmond degradation will probably allow you to meet in the middle and get the entire sequence. But a lot of proteins are not just 20 or 30 long. So there are two other reagents that are commonly used. And those are trypsin and chymotrypsin. And you may have talked about trypsin and chymotrypsin in biology classes. These are both serine proteases, which means that the catalytic triad in the active site consists of a serine, a histidine, and an aspartic acid. And they will break up your peptide in the middle. Trypsin cleaves the peptide bond at the carboxy end of your basic amino acids. lysine and arginine. And chymotrypsin cleaves peptide bond at the carboxy end of your aromatic amino acids. So phenylalanine, hydrazine, and tryptophan. And that allows you to break the long protein or peptide up into shorter peptides, which you then will sequence using the Edmond degradation and the Carboxypeptidase A. There are other enzymes that are used in protein sequencing that cleave next to, like, just the neutral alkyl amino acids, for example. But these two are very commonly used. They're both pancreatic enzymes from human pancreas, so they're easily isolable. They're both fairly stable. If I spell trypsin right. So phenylalanine, tyrosine, and tryptophan for chymotrypsin, lysine, and arginine, basic side chains for the trypsin, aromatic side chains for the chymotrypsin. That's a way of breaking up a big peptide into shorter peptides, and then you sequence the shorter ones using the 7 reagents that we talked about before. We're overdue for our break. Let's take one